Okay, so anion is negative, cation is positive. Okay, so this is a little trick to remember anions and cations. Cations has, if you write it out, cation, it has a plus sign in the word itself. Okay, anion. We know in a really general sense that atomic mass comes from the addition of protons and neutrons, right? However, why are the atomic masses on your periodic table not whole numbers? Right? Look at the atomic masses on your periodic table. Look at the atomic mass for magnesium. What is it? 24.3. Can we have a third of a neutron? Or a third of a proton? Right? That doesn't happen, right? So why aren't all of our atomic masses whole numbers? Okay? What happens is our elements occur as a mixture of isotopes. So we talked about isotopes being a version of an element that have different masses, right? And that means they have different numbers of neutrons. So if they have different versions of their masses, the atomic mass that you see on the periodic table is an average of those atomic masses. Some elements have 6 stable isotopes, some have 2, right? So it's an average of those occurring isotopes. Okay? So isotopes are atoms of the same element with different masses. You had that definition last class. You don't have to rewrite it. Okay, so the average atomic mass takes into account how much of each isotope is in a given sample. Okay, that means how naturally does this isotope occur, right? If you look at your periodic table, some of those elements that have atomic masses really close to a whole number means that one of their isotopes is much, much, much more abundant than the other. Okay, so taking into account oxygen. Take a look at oxygen's atomic mass on your periodic table. Okay, what is it? 15.999, right? We round it to 16 because it's so close. That means between oxygen's occurring isotopes, the most abundant has to be 16, right? But that means we also have an isotope that's at 15, right? Because we know that the isotopes occur between 15 and 16. Does that make sense? The oxygen 15 might only occur at a 0.1%, right? But it's there. Okay, so that's why our average atomic mass is just under 16. Okay, so that means if I take a sample of 1 million oxygen atoms, I might only have 2 that are oxygen 15. The rest are all oxygen 16, right? Which is why we consider it to be the most common. But if you look at chlorine, for example, take a look at chlorine's atomic mass. What is it? 35.45, right? That's really close to being kind of in the middle, which means that chlorine 34 and chlorine 35 share abundance a little bit closer, right? It's a little bit more of a true average there, okay? So average atomic mass, it's a weighted average. It's not just atom together divide by 2, right? Because we have to take into account how much of our isotope is in abundance, right? If it's 90% oxygen 16 or 99%, right, our average needs to lean more toward that 16. So it's a weighted average of the atomic masses. So here is our equation for calculating average atomic mass. Okay, average atomic mass. So we would take the percentage of our first isotope times the mass of our first isotope, plus the percentage of our second times the mass of our second, right? That could go on for as many isotopes as a certain element has. To remember when we calculate our average atomic mass is that if we have a number in a percent, so let's say we're at 98%, we can't multiply it by 98, right? We have to convert it to a decimal before we can multiply it through. So a 98% as a decimal point would be 0.98. Good. So that's just something that you got to think about. You can't just multiply it by 98%. Or the same thing occurs when it's at 0.1%, right? Just because it's already a small number doesn't mean we can leave it at a 0.1. So if it's a 0.1% occurrence, we have to make that 0.001 before we can multiply times our atomic mass. Okay, something to think about there. So this would be an example of finding copper. Okay, let's say 69.2% is a atomic mass of 62.9, and 30.7% has an atomic mass of 64.9. We average those together using our weighted average system, and we get out about 63.55. So I'll give you some examples that you can do the calculations. I'm just showing you how it goes in. Okay, there won't always be 3 isotopes. There won't always be a certain number, right? Every element has its own number of stable isotopes. So you'll just have to go with however many you're given. But the process is the same. So percent times mass plus percent times mass. Okay. Let's try this one here. Find the average atomic mass of an element that has the following occurrences. 87% at 33.212, 10% at 34.2, and 3% at 31.2. I usually take the final answer to 2 decimal places. I'm less concerned with significant figures at this point. Okay. So I converted those percentages to decimal places by moving the decimal 2 to the left. Multiply percentage times mass, and then we add them together. Okay, Alexa, what'd you have? 33.25. Good. And what's our units here? Good. Do we all agree? We get it to come out okay? All right, good. All right, next we're going to move on to molar mass. So we talked about atomic mass and molar mass. Okay, atomic mass and molar mass are calculated exactly the same way. Okay, the molar mass is technically a bigger scale of the atomic mass. Okay, so the molar mass is the mass of 1 mole of our substance. Okay, and the molar mass can be calculated of both elements and compounds. Okay, molar mass and atomic mass are calculated exactly the same way. So we'll talk about the difference here in a second. Okay, the molar mass of any given element is given on the periodic table because atomic mass and molar mass are essentially the same thing. They just are on a bigger scale. Okay, so if I ask you for the molar mass of oxygen, you're going to tell me 16, right, or 15.99. But the units for molar mass are grams per mole. Okay, the units for atomic mass are AMU, and the units for molar mass are grams per mole. So when we look at these two numbers, right, the numbers themselves are the same. But the units that we're talking about and the scale at which we're looking at these elements is different. Okay, so if I ask you for the atomic mass, that means that's the mass of one single atom. Okay, if I ask you for the molar mass, that means I'm asking for the mass in grams of 1 mole of our substance. Does anyone know what a mole is? Have we heard about a mole before? Okay, a mole is an extremely large number of atoms, usually, or elements, or whatever we're looking at. Okay? A mole could technically be a large number of anything. Okay? This is the number that, first of all, tell me, what's a dozen? 12, right? You know that right off the top of your head. Does it matter what substance I'm dealing with? Can I have a dozen baseballs and a dozen donuts and a dozen roses and whatever, right? Doesn't matter what substance I'm dealing with, a dozen is still a dozen, right? So a mole works the same way. Doesn't matter what I'm dealing with, a mole is just a much bigger number than a dozen. Okay, so think about it in terms of a dozen. It's a fixed amount, but it's much bigger. So 1 mole is equal to 6.022 times 10 to the 23rd of anything. Right, so that's a big number, times 10 to the 23rd. Right, that means there's 23, 20, really 19 zeros tacked onto the end of that number. Okay, so it's still a fixed amount. Right, 1 mole, I could have a mole of roses. It just means that I got, like, a whole school full of roses, right? So that's what we're talking about here. It's the same concept as a dozen, or as a baker's dozen, or as a whatever, term of measurement we understand, but it's just a bigger one, okay? So if I ask for the mass of a mole of oxygen, that means I want to know how many grams does this many oxygen atoms weigh, right? And so that's what the periodic table tells us. It tells us that if we take 6.022 times 10 to the 23rd oxygen atoms, it would weigh 16 grams. Okay? Just like one single oxygen atom would weigh 16 AMU. Okay, so the number itself is the same. The scale to which we're talking about them is just bigger. Okay? So it's important to understand that when we talk about molar mass, our units are grams per mole. Okay? So the average atomic mass of carbon is 12. The molar mass of carbon is also 12, right? But we're talking about it would be 12 grams of carbon would be equal to 1 mole of carbon. Okay, so when we say grams per mole, that means it's this many grams over 1 mole of our substance. We just drop the 1, right? Okay, does that make sense about molar mass? Kind of. Okay, same number. You just got to understand what units we're talking about. Are we talking about one single atom, or are we talking about a whole mole of our atoms? Okay, so we're gonna be able to determine the molar mass of our compounds now. The molar mass of an element is really easy because it's right on the periodic table. Molar mass of our compounds now, we're going to start adding the molar mass of all of our atoms within a compound. Okay? So to determine the molar mass of a compound, we're going to take into account every atom in there and its own individual molar mass. Okay, so let's look at H2O, for example. What's the molar mass of hydrogen? 1.008, right? When we find molar mass, like, I'm going to keep hydrogen at 1. Some people round it to 1.01. For our purposes, we're good with leaving hydrogen at just 1. Okay, so molar mass of hydrogen is 1. How many hydrogen atoms are in a water molecule? 2, right? So I'm going to take that times 2. So far I've got 2 grams of hydrogen. What's my molar mass of oxygen? 16. And how many of those do I have? Just 1, right? When I have no subscript here, that means my subscript is really a 1. So I've got 16 grams of oxygen in this compound. I've got 2 grams of hydrogen. So I add those together, and I get a molar mass of 18 grams per mole. Okay, the same would be true in atomic mass. If I took 2 hydrogen atoms and 1 oxygen atom, I would get an atomic mass of 18 AMU for 1 single water molecule. Okay, but we deal with the units molar mass much more regularly. Okay, it's much more usable scale for us, right? We deal with grams. We don't deal with atomic mass units. So this will be the more common version we see. Okay, 18 grams per mole. Are we good with where all those numbers came from? Okay. Okay. Blah, blah, blah. We already talked about that. Okay. Sometimes compounds are written with parentheses, which we haven't quite seen yet. but I'm going to show you what we're talking about here. If we've got bigger compounds that have multiple atoms, we'll see compounds written with parentheses. Okay? So this is the rule for items with parentheses. Okay? The number outside the parentheses multiplies everything inside by that number. So we're like distributing that subscript. We're not just adding those together, right? When you distribute something through parentheses, what does that mean you do? You multiply, right? That's what we're doing here. Okay? So it multiplies everything inside by that number. Okay, so this is a compound called iron sulfate. So we're going to try to find the molar mass of iron sulfate. This is a little more complex than water, right? It's got more atoms and it's got more atoms in general. Okay, so let's look first at iron. How many iron molecules do we have? Okay, and what's the molar mass of iron? Let's keep them at 2 decimal places. 55.84. Okay, 55.8. Technically, that last one would round, so we're at 8.5. Okay. Okay, so if I multiply those together, that gives me at 111.7. So I've got iron done so far. So now I'm going to go individual elements. I have how many sulfur atoms?
1. 4. Now 3. 1.
I have 1 right here, but I've got 3 of those individual sulfate molecules, right? This molecule is sulfate, and it's saying I have 3 of them. So that means this 3 gets distributed. So that means I have 3 sulfur atoms. Okay, and the atomic mass of sulfur is 32. Okay, lastly here, I have oxygen. How many oxygen atoms do I have? 12 or 7? 12. We multiply that, right? So if each sulfate molecule has 4 oxygens, right? So 4 oxygens here. We have 3 sulfate molecules. So 4, 4, 4. Right? That gives me 12 total oxygens. Does that make sense? We've got to picture what's happening in the molecule itself. So sulfate is what that compound is that's inside the parentheses. It itself has 4 oxygens. So if we have 3 of those molecules separately, that means that we've got 12 oxygens going on. Okay, so we have 12 times 16, 192. We're going to add those together. Agreed? Okay, so if I took a whole mole of this iron sulfate molecule, it would weigh almost 400 grams. Right? So some compounds are much, much heavier than others, right? Water, not so heavy compared to this one, right? Questions here? Okay, do we understand the parentheses concept? It distributes, it does not add. Okay, we'll still have, some of you will try to add those. And it's just a simple mistake, but just make sure we're paying attention that we should distribute that through there, not no addition. Okay, so multiply there. Uh-huh.
But you're still adding the iron, right? Is it just...
You still add each of the individual atoms together, but I'm talking about when we're trying to find the number of oxygen atoms that we have, we multiply those 2 together.
That only applies to this one.
It only applies to the parentheses number. Yeah, we have 2 of these. The subscript always tells how many of those atoms we have, or in this case, how many of the compounds we have. Okay. Okay, go ahead and try these on your own. Okay, let's make one little note here. If there's no parentheses, where does this subscript belong? Just to the oxygen, not to anything else. So, and without any parentheses, your subscript just goes to the element directly in front of it. Okay, so without parentheses, we don't distribute anything. It's just exactly what's given. Yeah, 2 decimal places is fine. Okay, so percent composition has to do with what percent of this compound is made up of oxygen atoms. And we're not talking about like the ratio of oxygen atoms, 2 to whatever. We're talking about what percent of it by mass is made up of oxygen atoms. Or what percent of it by mass is made up of sodium atoms, things like that. Okay, so we're looking at what percent of this compound is made of a certain element. Okay, so we're going to be able to compare the mass of the element itself to the mass of the entire compound. So we have to be able to calculate molar mass before we can calculate percent composition. Okay. So the first question I'm going to ask is I want you to find the total percent composition of sodium chloride, which means you're going to find the percent of sodium and you're going to find the percent of chlorine, right? That's the percent composition. If I ask you for the total percent composition, you're going to give me every element in there, okay? And so this is how it works. You're going to find the total mass, the total molar mass of sodium chloride first. Okay, so before you can do anything, you got to find molar mass of sodium chloride. Okay, so this is percent composition. Find the total molar mass first, which is 23 plus 35.5, 58.5 grams per mole. Sodium. So I'm going to find the percent of Na. How do I find the percent of anything?
Divide.
I take the part divided by the whole. Okay, part divided by the whole. So I would take the molar mass of sodium itself, which is 23, divided by the whole, 58.5. Okay, so even though this compound is made of one atom to one atom, it doesn't mean that the mass is distributed evenly, right? Chlorine weighs a lot more than sodium. So within the atom itself, 39.3% of it is sodium, and what percent of it is chlorine? 60.7. So you can do this two ways, right? Since we know our compound is only made of two elements, we can just subtract this from 100%. But here's the problem. If you calculated this one wrong, then your other one is calculated wrong, right? So you can either just go back and do percent of chlorine by 35.5 divided by the whole, right? And we would get that as well. This numbers should add up to 100%, right? That's the goal. They should be adding up to 100% or very, very close to it, depending on where you round that decimal place up, okay? So if I ask you for percent composition of a compound, you're going to give me all the elements. I may have just asked what's the percent of sodium in sodium chloride, and then you only have to do one. Okay? Oops. Okay. What is the percent mass of calcium in this calcium nitrate compound? Okay, you're going to find percent mass of only calcium in calcium nitrate. So that means I don't really care what the percent of nitrogen or oxygen is. I only care about calcium. Okay, so it starts first by finding molar mass, then by taking calcium divided by the whole. Okay, so the total molar mass of calcium nitrate was 164.1. We took 40, which was the mass of calcium itself, divided by the whole, and we got 24.4%. Perfect. Okay. I'm going to have you try a couple here on your...
Are we like finding out the whole thing?
Yep, so if it just asks for percent composition, you got to find all of the compounds. If, like in this one, I say just percent of magnesium, that's all you have to find. Okay, so the first one, you got to find the percent of lithium and phosphorus and oxygen. Okay, so go ahead and try both of those on your own here. Oops. Sorry. My bad.